Hello guys, in the last lecture we seen the types of polarization and the few are remaining. Today we are going to cover that part, and in the last lecture we seen the types of polarization as electronic polarization, ionic polarization and orientational polarization. So we continue with this part. Today we are going to see the combined polarization and interfacial polarization. Let's see first combined polarization. The total polarization of a polyatomic gas is given by simply the sum of all the three types of polarization. That three types are nothing but electronic polarization, ionic polarization, and the last one, orientational polarization. So the sum of these all the polarization is nothing but combined polarization, and that total polarization of a polyatomic gas is given by P is equals to N into bracket alpha E plus alpha I plus PP square upon 3K into T into capital E. Alpha E is nothing but electronic polarization. Alpha I is from ionic polarization, and the third term pp square pp square upon 3 into k into t. This term indicates the orientational polarization. By combining this with the result of the macroscopic theory, and we've seen the equations of electronic polarization, ionic polarization, and orientational polarization. If you're combining this, and also we have the relation for relative permittivity in terms of molecular properties, as we can define as epsilon 0 into epsilon r minus 1 is equals to n into alpha e plus alpha I plus pp square upon 3k into t. Just it is nothing but the equating the equations of polarization. If we are multiplying here also E, this is nothing but total polarization also in terms of uh, permittivity, which includes the relative permittivity and permittivity for vacuum or free space. And if we are writing on the side right hand side also multiplying with the E, we showing the total polarization as we seen in this equation. Just by equating these equations, we will get the relation of polarization and with relative permittivity. We are here focusing with the relative permittivity because the relative permittivity is depends on the semiconductor material or dielectric material. As the dielectric material changes, their relative permittivity also changes. That's why the polarization is completely depends on the type of material, as it depends on with dependency with relative permittivity. As this last equation enables us to separate the alpha E and alpha E plus alpha I, and this PP square. Alpha E and alpha I are practically independent of these two terms, are the independent of temperature. Whereas the third term, that is PP square upon 3 kT, which is implicitly read as alpha O, that is orientational polarization, and which is dependent upon the temperature. So if you are going for the plotting of total polarization, which equating with the alpha epsilon 0 into epsilon r minus 1, then we will get the plot as with respect to temperature as here. This is on the x-axis, we are considering 1 upon T, that is temperature term, and on left hand side on y-axis we are considering alpha 0 into alpha r minus 1. Initially it is, you can see here the graph started from a non-zero value here, and this term indicates the polarization, the value of polarization which is not dependent on the temperature, that become that always present, that is n into alpha E plus alpha I, means electronic polarization and ionic polarization. And this slope, additionally this slope is become a straight line, and that slope is nothing but n into pp square divided by 3k, and we conclude that the slope of this polarization with respect to the temperature is a straight line. Now next we will see the interfacial polarization. The three mechanisms of polarization characterized by an electronic polarizability, an ionic polarizability, and an orientational polarizability. And due to the charges that are locally bound in atoms, in molecules, or in the structure of solids and liquids. In addition, the charge carriers usually exist that it can migrate for some distance through the dielectric. Free charge carriers migrating through the crystal under the influence of an electric field may be trapped by or pile up against the defect, such as lattice vacancies, impurity centers, dislocations, and so on. The effect of this will be the creation of a localized accumulation of charges, which will induce its image charges on the electrode and give rise to dipole moments. This constitutes a separate mechanism in the dielectrics, which is called as interfacial polarization, which is indicating with the capital P in the suffix S. Here you can see PS. Here a figure shows with E is equals to 0 and E. That figure indicates how the charge carriers may pile up at the interfaces or at the electrodes and give rise to space charges and a microscopic field. When the electric field is absent, the charges are arranging in the random manner You can see here with alternating, this is a positive charge, then appearing negative charge, again positive charge, then again appearing negative charge, positive charge, again it's appearing negative charge. Like that it is appearing with the alternating charges, means random movement of that charges appearing when electric field is absent, that is E is equals to 0. But as compared to this figure, we are going to turn to this figure which is having electric field. As electric field applied, the negative charges and the positive charges are coming in the uniformity. So you can observe that this most of the charges appearing with the grouped into a single charge, and positive charges also grouped into a single charge, but few of that charges are coming into the random motion, that called as minority charges. The total polarization can be considered as still we have the total polarization with including the interfacial polarization. Here we can calculate the total polarization, or we can write the equation for total polarization, that is P is equals to PE plus PI plus PO plus PS. What it means? Simply, it is a sum of all polarization. First is electronic polarization, second ionic polarization, third oriental polarization, and fourth interfacial polarization. And for a single phase dielectric containing permanent dipoles, which is having a permanent dipole, for that permanent dipole the interfacial polarization should be absent. That's why this equation becomes P is equals to PE plus PI plus PO, and it could be write as PE plus PI can be indicated with the alpha E plus alpha I into E. This is nothing but total dipole moment of with consideration of all polarization. So N into alpha E plus alpha I into E, this part indicates the dipole moment with consideration of electronic polarization and ionic polarization. The second part is nothing but the orientational polarization. This is nothing but orientational polarization. Next is we are going to turn towards types of dielectric materials and their static dielectric constants. As we discussed in the last and this lecture earlier about the major polarization types, that are nothing but the three major sources, that are electronic polarization, ionic or atomic or molecular polarization, and third is orientational polarization. By considering this polarization, these are we can be write as the total polarization as P is equals to PE plus PI plus PO. This is simply sum of the total dipole moment is nothing but the sum of the different main sources of that types of polarization, that is PE electronic polarization, PI ionic polarization, and PO orientational polarization. This relationship provides a means for differentiating among various important groups of dielectric materials. One type represents the case in which the principal effect is electronic and the ionic, and dipolar components are negligible or zero. Another class consists of those materials in which the contributions are from electronic and ionic sources with no dipolar component. A third class is one that includes the components arising from three sources given in this equation. The materials may be categorized as non-polar and polar materials. Non-polar material is one which does not have permanent dipoles like carbon or diamond, and H2, that is a liquid. A polar material is one which has permanent dipole moment. For example, sodium chloride, that is rock salt, you can say. Then rutile, quartz, silicon oxide, so, and also soda glass. Some materials like polythene, paraffin, polytetra fluoroethylene are weakly polar. And there are three types of dielectric materials, means three classes of materials may be identified as far as the dielectric behavior of the solids is concerned. The first is elemental solid dielectrics. Second, ionic non-polar solid dielectric, and third is polar solids. If you are concerning with the behavior of solids as a polar and non-polar, then first elemental solid dielectric has the solids exhibiting only electronic polarability. That material are nothing but elemental solid dielectrics. And the solids which manifest the electronic and ionic polarizabilities, that solid materials are nothing but ionic non-polar solid dielectrics. And the solids which possesses orientation as well as electronic and ionic polarized ability, that solids are nothing but a polar solids. Thank you very much.